Alright, hello and welcome everyone to the lesson on solving inequations. So in this lesson, there's 4 different types of inequations we're going to look at. As you can see below, we have the basic linear, quadratic, absolute values, and inequations involving variables on the denominator. Alright, so let's look at type 1, our linear equations. So ultimately these ones here are really simple. You can just solve them like normal, but just make sure you reverse the inequality anytime you multiply or divide by a negative. All right, let's have a look at our first example. So if we were to solve this equation, here we go. So the idea is, just go ahead, solve using your normal steps, multiplying by 3. Next step, we're now going to add 1 to both sides. And finally, divide by 2. In this case, at no point have we had to times or divide by a negative, so that inequality remained greater than or equal to the whole way through, and you end up with the solution. On to our next example. So this is another linear equation, right? The x's are represented, there's no square roots or squares attached to the x's. And again, we're just going to solve it just like normal. So in this case, we've got x's on both. I'll rewrite it again. Okay, so we've got x's on both sides. So let's take that 4x across to the other side, giving us a negative 2x. Take that minus 1 across, adding 1 on. And now this final step, we're going to need to divide by negative 2. Since we are dividing by a negative, I'm going to need to make sure I flip or reverse that inequality. So our final solution ends up becoming x is less than 1. All right. Our second type are the quadratic inequations. So there's a couple different methods here. We have the critical values method, which is where you find the critical values. Those critical values will break up the number line into different regions, at which point you then just test values that belong to each region to work out which regions satisfy the inequation, and then you get to write down a solution. The second method is mathematically identical as far as difficulty. The only difference is instead of testing the regions, you end up drawing a graph of the quadratic, and then instead of having a test, you can just see, just visually on the graph, which regions satisfy the inequality, and of course you'll end up with the exact same solution, no matter which method you use. So let's have a look at this first one here. I'll use the critical values method for this one here. Let's say we want to solve this inequality. With the critical values, to find them, ultimately you ignore the inequality and just pretend it's an equals. So in other words, you have x squared is equal to 16, and you just go ahead and solve this to find your critical values just like you would normally. You could take the 16 across and factorize down if you wanted. Difference of 2 squares. And of course, you'll end up with critical values of 4, or x is equal to a negative 4. Coincidentally, it would have been a little bit easier, admittedly, just to square root and just get the plus or minus 4 straight away from the original one. It doesn't matter which way you do it. You should end up with your critical values of a 4 and negative 4. From that point, if I just draw up a quick number line here, I've got minus 4 over here, a positive 4 over here. We can see that the number line has been split up into 3 different regions. The first, second, and third regions. And all we need to do is just plug in some different test values from each region to determine which region satisfies the inequality. So for the first region, I'm just going to let x equal minus 5. So plug that into our original equation up here. So in this case, minus 5 squared, that will become 25 is less than 16, which you can see is not true. The first region fails. Let's look at the second region. So let's pick any value we want in between -4 and 4. For simplicity reasons, I'll choose the value 0. So plugging 0 up into our inequation, we end up with 0 squared is less than 16. Is 0 less than 16? Yes. This second region ended up holding true. So this is part of our solutions, that whole region from -4 to 4, and testing the third region is going to fail. Let's pick a value, let's say 5 for example, and you end up with a similar situation of 25 is less than 16, which is just not true. So using those critical values, we have determined that it is this middle region, which is part of our solution. So we would write down x will be all values from -4 right up to +4. That would be our solution there. All right, let's have a look at another quadratic. But this time we'll use the sketching method just so you can see. So if you were to solve this one here, using the second method, you would let y equal x squared minus 2x minus 15. You're stuck having to ultimately do the same mathematics anyway, which is solving this equation, right? In this case, I'm finding the x-intercepts, but these x-intercepts will ultimately be our critical values. So once I get to this point here, I can sketch our parabola. It doesn't need to be super neat, right? There's no marks for the sketch. This is just part of our working out to get the solutions. But we have an x-intercept at 5 and -3. So it's some sort of parabola that looks like this. And we're trying to find the inequation says, when is this parabola greater than 0? So when is this parabola greater than 0? That occurs in, see, the x-intercepts have ultimately created 3 regions, and the parabola is greater than 0 out in this first region and this third region. So our solutions for this one would be x is less than or equal to -3, or x is greater than or equal to 5. So that would be our solutions for this second one using the graph method. Now, if you're a massive fan of critical values, again, what would you do differently? You forget about the inequality, pretend it's just a normal equation, replace the inequality with an equal sign. Go ahead and solve that equation just like you normally would to get your solutions. In this case, it's -3 or it's +5. So these are our critical values or critical points. These critical points break the number line up right here at -3 and over here at +5 into 3 different regions. And again, what you would need to do is to determine, well, which of these regions are part of our solutions. You would just pick any value that belongs to the first region and test it in the inequality. So in this case, I might let x equal -4. So plug in -4 into our original equation, we end up with 16 plus 8 minus 15 is greater than or equal to 0, which this ultimately ends up being true. The first region is part of our solution. When you test an x value belonging to the middle region, in this case I've chosen 0, you end up with something that is not true. And if I test a value from the third region, maybe I'll let x equal, let's just say it's 10. Right? It can be any value from that third region. You'll end up with some value or some expression, I should say, which ends up being, in this case, true yet again. So, using the critical values, we have determined that the first region and third region belong to our solutions. So, in other words, x is less than or equal to -3, that third region, or x is greater than or equal to 5, which was our third region, which, not surprisingly, gives you the exact same solution no matter which method you use. All right, on to our third type. These are the absolute value type of questions. And, there's two different methods here. The critical value method, what I've listed as method 2, that's the one most of you will probably mostly prefer to use. Method 1 actually is a little bit quicker though, admittedly, and I'll show you how that one works as well with this next question. So let's say you wanted to use the critical values method for solving this inequation here. So what you would do is you would pretend that the inequality doesn't exist. Just replace it with an equal sign and just solve this thing like normal. In this case, however you end up doing it, you end up with, I'll use the positive and negative case. We're actually going to end up with two different critical values here, just like we did with the other couple questions. So add 1 to both sides, divide both sides by 4, you end up with -1/2. Okay, so we've found our critical values. Two critical values, that will of course split the number line up into 3 different regions. Over here I've got -1/2. Somewhere over here I've got the value 1. So we have our first, second, and third regions, and all we need to do is test a value from each of the 3 regions into the original equation to see which regions are going to form our solutions. So our first region, I'm going to let x equal -1. I'm going to plug that into our equation. We end up with, what was that? The absolute value of -5 is less than or equal to 3. The absolute value of -5 is 5, of course. Ultimately, we end up with something which is incorrect, it's false. That first region is not part of our solution. If I let x equal 0, you plug it in, so sub 0 into the equation, work it all out, and you're going to end up with 1 is less than or equal to 3, which is true. And let's pick a value from the third region. I'm going to let x equal 2. In this particular case, you end up with 7 is less than or equal to 3, which is false. So from the critical value method, we can see it's the second region which will belong to our solutions. In other words, -1/2 is less than or equal to x, which is less than or equal to 1. That's our solution right here, using critical points or critical values. Okay, so if that's the way you want to do it, the method works, right? You end up with the correct solutions. Just to show you what was mentioned here over here in method 1, if the absolute value is less than a, you can actually rewrite it as just one equation straight away. So if the absolute value of this is less than or equal to 3, then that means this will be less than or equal to 3. But it would also need to be greater than or equal to -3. Right, this is what I've used here, the less than or equal to 1. It's a little formula you can remember if you want. What it does do, if you remember it, is it makes finding our solution way quicker. Solving this is so simple. We're trying to get x by itself. So if we look at this middle section here, how are we going to do that? Let's add 1 onto everything. Add 1 onto this. Adding 1 onto this will cancel that -1. And adding 1 onto this will give us a 4. Our final step to get x by itself is going to be to divide everything by 4. Divide this by 4. Divide this by 4. And divide this by 4. You end up with the exact same solution in a far more efficient manner. So if you do have a good memory and, you like to make things as easy as possible, it really might be worthwhile investing into these two expressions here, knowing how to write them out. The first one, it all just becomes this one really cool inequality. In the case when you're dealing with a greater than or equal to, it ends up getting split up into two separate equations. But again, it's going to be quicker than the critical value method. However, if you like just one method, which is always going to work, critical value, it works, takes longer, but does give you correct solution. All right, on to our final type. What do you do when the variable's on the denominator? So typically the main method is to multiply both sides by the denominator squared. And the whole idea of that is it avoids us having to deal with the scenario of what if the denominator is negative? So if you were just to solve this inequality as it stands, like if it was a normal equation, for example, you would take that x minus 4 over to the other side, right? By ultimately multiplying by x minus 4. The problem here is we know since this is an inequality and not just an equal sign, if x minus 4 is a negative, we would need to reverse that inequality and make it a less than or equal to. But we don't know whether it's positive or negative. So we use the trick of forcing it to be positive. We're going to multiply everything by x minus 4 all squared. And what's great about that is, a number squared will always be positive. So we can do that and we won't need to worry about flipping our sign. So multiplying this first side by x minus 4 squared will ultimately get them to cancel. I can keep this as a greater than or equal to because I know I've multiplied by a positive here, and multiplying the second side by an x minus 4 squared leaves us this. So we end up with 5x minus 20 is greater than or equal to, expanding this out, this. I'm going to move everything across to this side over here, just because I want that x squared to be positive, to be honest. All right, that 5x coming across would make it a minus 13x. That minus 20 coming across will be 16 plus 20. And I'm now going to rewrite it in the normal way we're used to seeing it. I can just reverse these here. By flipping them around, so now I've got a less than or equal to 0. Okay, so by multiplying both sides by x minus 4 squared, ultimately this thing has just become a type 2 inequation, just like we saw back over here. It's just a standard quadratic inequality. And again, use whichever method you like. For me, I'll do a graph just because there's a little bit less writing to do with the graphs. So I've factorized it down. A quick little mini sketch. Doesn't need to be to scale. Okay, so I've got some sort of parabola that's looking like this. We're trying to determine when this parabola is less than or equal to 0. I can see that occurs in the second region, right? Again, we've got these critical values that have split our number line up into 3 regions. And from the graph, we're below 0, we're less than 0 in the second region. So in other words, our solution will be 4 is less than or equal to x, which is less than or equal to 9. If you really love critical value method and you wanted to solve this using critical value method, again, it works for this particular type of question pretty easy. I might just throw in one extra page just to show you how that works. So I believe the original equation was this. Yep. Okay, so how would you solve this using critical value method? Well, the first thing to note, actually, I need to go back because I've just made a mistake with my solution here. So in this particular case, it's worth noting that there's a particular restriction on our solutions. When we go back to, hey, we've got a variable on the denominator, x minus 4 is on the denominator. That tells us that x minus 4 is not allowed to equal 0. Right? This inequation does not have a solution when x minus 4 is equal to 0, or in other words, when x is equal to 4. So in other words, x is actually not allowed to equal the value 4. So I actually need to go back up to my solutions here, because I actually do have the value 4 included in my solutions. That right there will fix it up. This here is the correct solution, and definitely worth noting. By the way, that wasn't like a intentional mistake just to illustrate the point. That was a genuine mistake I just made then. So definitely keep that in mind. Using our critical value method. So the idea with the critical values, you know what it is. You just ignore the inequality, pretend that thing is an equal sign, and you just solve the equation like normal. 5 is equal to x, so I take that x minus 4 across to the other side. You solve the equation, you get x is equal to 9, right? Notice that actually is one of our critical values. But this one had 2 critical values. Where do you get the second critical value? Well, it actually comes from, we know that x minus 4 is not allowed to equal 0. So solving this separate thing will actually end up giving you your second critical value. And then you just go ahead, just like we've been doing, test the 3 regions, see which regions work out, which funnily enough ends up happening to be the second region. You'll get failures in the first and third regions, which we know that because we've got the graph over here telling us it is the middle region. So just be aware, critical value method can work for that. In actual fact, you could use critical value method for every single question. And I mean, going right back, you could even use it for, type 1 equations, this one or this one. You could replace that equal sign, the inequality with an equal sign, go ahead and solve. Well, we know what it ends up being, right? You end up with x is equal to 6.5. Here I'll write it as a decimal this time, just for some variation. And from there we've got one critical value at 6.5. One critical value ultimately breaks the number line up into just 2 regions, the first and second. And of course you could go ahead and test. Pick a value from this region, it'll fail. Pick a value from the second region, some value greater than 6.5, and it will pass. And of course, you'll end up getting the exact same solution. Of course, I'm not recommending you use critical values for type 1 because they're much easier just doing it as we did. But just sort of keep that in mind. If you really love critical values, you could actually use that critical value method for every single type of question you see here in this video. Anyway, we're going to leave it there. Hopefully this was helpful, and I'll see you guys next time.